Everything we do is available on BioniChaos.com. Go check the website out. Let me know if there is any feedback. Don't forget to like, subscribe, unsubscribe, whatever you have to do. And check Patreon as well if you want to support this project.
You know that feeling, like information overload? Your brain just feels jammed, signals all tangled up, data looking like a complete mess. But what if, right? What if you had this like mathematical superpower, kind of secret decoder that could just untangle it all, reveal the pure, simple bits hidden inside?
It does sound a bit like science fiction, doesn't it?
Yeah.
But that superpower, it actually exists. It's called the Fourier Transform.
Fourier Transform. Okay. Sounds a bit intimidating, like something off a physics blackboard.
Yeah, it can sound that way.
Right.
But honestly, it's not some scary abstract thing. It's actually a surprisingly elegant idea.
Wow.
And it pops up everywhere.
Everywhere.
Oh, yeah. Way beyond just sound and frequency. You find it in all sorts of areas of science, engineering, areas that seem totally unrelated at first glance.
Oh, okay.
So our mission really in this deep dive is to give you a clear introduction, to kind of demystify it, show you how it works, and just how incredibly useful this one single concept is.
A shortcut to sounding smart about signal analysis.
Well, maybe. Consider it a shortcut to being genuinely well-informed on, honestly, one of the most transformative ideas out there.
Okay, let's unpack this then. Let's start with sound. That seems like a good place.
Perfect. So imagine a really simple, pure sound, like the note A. That's 440 vibrations or beats per second.
Right.
If you could see the air pressure change, it would be this nice, clean, smooth wave going up and down. Predictable.
And a lower note, like a D.
Same idea. Just, fewer waves per second, slower oscillation. Still pretty straightforward.
Okay. Simple enough. One note, one clean wave.
Exactly. But what happens when you play both notes, the A and the D, at the exact same time?
Okay. Things get messy.
They do. The air pressure graph, it's not that neat wave anymore. At any single moment, the pressure is just the sum of what the A would be doing plus what the D would be doing.
Just sometimes they add up, sometimes they cancel out a bit.
Precisely. Peaks might line up, making it louder. Or a peak might meet a valley, and they sort of counteract each other. The result is this. Well, it's still wave-ish, but it's definitely not a pure, simple wave. It gets, as the source material puts it, kind of a complicated thing to think about.
Right. And I guess if you add more notes or like background static or something.
It just gets worse. More and more tangled. It can start to feel, needlessly complicated when you think about the simple notes you actually put in.
Because your ear or a microphone, it doesn't hear the separate A and D waves, does it? It just gets the combined result.
Exactly. It only registers that final jumbled sum.
Yeah.
So that brings us to the core problem, the real challenge here.
Which is?
How do you take this messy-looking signal, this complicated sum, and figure out which pure frequencies actually made it up in the first place?
It's like someone mixed blue and yellow paint together to make green, and now you want to get the pure blue and pure yellow back out again?
That's a great analogy, yeah. Pulling them back apart feels exactly like trying to unmix paint. Seems almost impossible.
Some kind of trick, yeah.
And what's fascinating is our ears, they do this separation automatically, effortlessly, but mathematically. Those sounds just merge into this complex mush.
So we need that mathematical trick, that unmixing machine.
Precisely. We need to build a conceptual mathematical machine. And its main strategy has to be treating signals of one specific frequency differently than it treats all the others. It needs to pick them out.
Okay, how does it do that? This sounds interesting.
This is where it gets really clever and maybe a little abstract visually, but stick with it. The core idea is you take your signal graph, that wiggly line over time, and you sort of wrap it up around a circle.
Wrap it around a circle. How does that work?
Okay, imagine you have like a little spinning arrow or a vector starting from the center of a circle. At every point in time on your signal graph, you look at the height, the value of the signal. The length of your little rotating arrow at that exact moment is set by that height. So if the signal is high, the arrow stretches further out from the center. If the signal is low or negative, it shrinks closer in, maybe even points the other way.
So the timeline gets turned into a spiral or some kind of pattern around the circle.
Exactly. It's like transforming that linear time into this dynamic rotating picture.
Okay, I'm picturing it. It sounds potentially complicated.
It can look complicated, yeah.
Yeah.
But here's the crucial bit. There are actually two different frequencies involved now.
Two?
Yeah. First, you have the frequency that might be in your original signal. Like if you play that A note, There's a 440 beats per second frequency in there.
Right, the sound itself.
And then, totally separate, there's the frequency of how fast we choose to wrap the graph around the circle. Let's call that the winding frequency. And we can change that. We can wind it slowly or really fast.
Ah, okay. So one frequency is baked into the signal, the other is a dial we can turn on our wrapping machine.
You got it. And yet the diagrams you get when you do this wrapping could look pretty complicated, but sometimes they're also very pretty. But always remember, fundamentally, all that's happening here is that we're wrapping the signal around a circle. We're just changing its representation.
Okay. So we wrap the signal around a circle at a speed we choose. Why? What does that do?
This is where the magic starts. You get this feeling, this intuition, that something kind of special ought to happen if the speed we choose for wrapping our winding frequency perfectly matches a frequency that's actually in the signal.
Like if the signal has a strong 3 beats per second rhythm, and we set our winding speed to exactly 3 cycles per second.
Exactly that. When those two match, something amazing happens in that wrapped up picture. All the high points from the original signal, they consistently land on one side of the circle, let's say the right side, and all the low points, they all gather on the opposite side, the left.
Whoa, okay. So it like sorts itself out.
It does. It's this beautiful alignment that only happens when the winding frequency hits a frequency present in the signal.
That's the trick. That's how the machine tells things apart.
That's the core mechanism.
Yeah.
Now take it one step further. Imagine that wound up shape, that pattern on the circle.
Mm-hmm.
Imagine it has some mass, like it's a bent piece of metal wire.
Okay, like a physical object now.
Yeah. And what we're interested in is its center of mass, the balancing point of that shape.
Right.
Now, for most winding frequencies, when the signal is wrapped up, the high points and low points are probably scattered all over the place, more or less evenly.
So the center of mass would be near the middle.
Pretty much. It might kind of wobble around a bit, but
Okay.
it stays pretty close to the origin, the center of the circle. It's all averaged out.
What about when the frequencies match? When everything lines up on the right and left?
That's the aha moment. Because all the heavy bits, the high points are on the right, and the light bits, low points are on the left, the overall center of mass gets pulled way over. It's unusually far to the right.
It jumps out.
It jumps out. It's like that hidden frequency is suddenly making its presence known, physically shifting the balance point.
Okay, that's cool. So what do we do with that?
We track it. For every possible winding frequency, we try slow, medium, fast. We calculate where that center of mass lands. Specifically, we can just plot its horizontal position, its x-coordinate.
And what does that plot look like?
You get a graph. And on this graph, you'll see a big, sharp spike right at the winding frequency that matched the frequency in your original signal. For our example, a spike at 3 cycles per second.
So the graph pinpoints the hidden frequencies.
Exactly. Oh, and sometimes you might see a big spike around 0 frequency. That just means your original signal had an overall average value that wasn't 0, like it was shifted upwards. It doesn't represent an oscillation, just a constant offset.
Gotcha. So this graph, the plot of the center of mass's x-coordinate versus winding frequency, that's the Fourier Transform.
It's almost the Fourier Transform. We call it that in the source, kind of informally. It captures the main idea, just a tiny step away from the real deal. But this center of mass idea, that's the heart of it. It's the indicator. It's how we find the hidden stuff.
And does this work if there's more than one frequency in the original signal? Like our A and D notes played together?
Yes. This is where the machine becomes really delightful. Let's take that combined signal, the sum of, say, a 2 beats per second wave and a 3 beats per second wave. It looks more complicated, right?
Yeah, that jumbled mess.
Now feed that into our winding machine. As you slowly increase the winding frequency, wrap that complex shape around the circle. Yeah, it looks pretty chaotic most of the time. Just a tangled mess.
Chaos.
Chaos and chaos and chaos and chaos and chaos, as the source vividly puts it. But then, whoop! Suddenly things seem to line up really nicely when your winding frequency hits 2 cycles per second. The center of mass jumps out to the side.
Spike number 1.
Spike number 1. Then you keep increasing the winding frequency. More chaos, more tangles. Chaos and chaos and chaos and chaos until whoop, things nicely align again when you hit 3 cycles per second. Center of mass jumps out again.
Spike number 2. It found both frequencies.
It found both. It's almost funny how well it works. That visual chaos resolves into perfect clarity at just the right moments. We've gone from the jumbled sum back to a clear readout showing peaks at 2 hertz and 3 hertz. We found the ingredients. We unmixed the paint.
Okay, why does it work so well with multiple frequencies. Is there a reason it separates them so cleanly?
Yes, there's a fundamental mathematical reason called linearity. It sounds technical, but the idea is simple.
Lay it on me.
Okay. Imagine you take the 2 hertz signal, find its almost Fourier transform, that center of mass plot with a spike at 2 hertz. Then you do the same for the 3 hertz signal, getting its transform, spike at 3 hertz. Now, add those 2 transform graphs together.
Okay, so I'd have a graph with a spike at 2 and a spike at 3.
Exactly. Now, linearity means you get the exact same result if you first add the 2 hertz and 3 hertz signals together, making the complex wave, and then calculate the transform of that combined wave.
Whoa, so transforming separately and adding is the same as adding first and then transforming.
That's linearity.
Yeah.
And it's super powerful because we know the transform of a single pure frequency is basically 0 everywhere except for that one spike.
Right.
It means the transform of a sum of pure frequencies is just the sum of their individual transforms. You just get this clean graph with little peaks sitting right above the frequencies that went into the original mix.
So the machine really does just perfectly pull out the original frequencies from the jumble. The paint unmixing works?
It works beautifully. It does exactly what we wanted.
Okay, this is clearly powerful for analyzing sound, but you said it goes beyond sound.
Oh, absolutely. This isn't just about audio. The same core idea, breaking down a complex signal or pattern into its fundamental frequencies or components, is used everywhere. Think about JPEG image compression.
How you shrink photos down.
Yeah. Part of how that works involves a 2D version of the Fourier transform. It breaks the image down into different spatial frequencies, like broad areas of color versus fine details. Then it can sort of throw away some of the less important frequency information to save space.
Huh. So it's finding the frequencies of patterns in a picture.
In a way, yes. Or think about medical imaging, like MRI scans. Those machines measure signals from your body, and they use transforms very similar to the Fourier transform to turn that raw data into the detailed images doctors look at. It's about converting signals measured over time or space into a frequency representation that makes sense visually.
Wow. Okay. Seismology, quantum mechanics. You're saying this idea is fundamental.
It really is. It's one of the essential tools for analyzing patterns and signals in so many fields.
Can we look at one practical example, maybe back with sound, like getting rid of noise?
Good idea. Yeah, sound editing is a perfect example. Let's say you have a recording maybe of speech, but there's this annoying high-pitched whine in the background.
Okay, happens all the time.
Right. So your original recording is just sound intensity changing over time. Now you apply the Fourier transform. What do you expect to see on that frequency graph?
Well, I'd see the frequencies that make up the speech, presumably. And, that annoying whine would show up as a sharp spike at whatever high frequency it is.
Exactly. It stands out clear as day on the frequency plot. So if you want to filter it out, what do?
You just erase that spike, or maybe you just squash it down.
Precisely. You digitally manipulate the transform graph. You find the spike corresponding to the whine, and you just reduce its height, effectively smushing the spike down.
Okay, so now I have a modified frequency recipe without the annoying ingredient, but that's not sound, that's still a graph.
Right, and this is where the symmetry comes in. There's also something called the inverse Fourier transform.
The way back.
The way back.
Yeah.
It takes your modified frequency graph, the one with the whine removed, and it tells you exactly which time domain signal would produce that specific frequency fingerprint.
So it reconstructs the sound, but without the whine.
Bingo. You transform to the frequency domain, do your editing there, like removing noise, and then you transform back to the time domain to get your clean audio signal. It's like unmixing the paint, removing the bad color, and then perfectly mixing the rest back together.
That's incredibly elegant.
It is. Now, the source does add a little note here saying calling it a perfect inverse is a little bit of a lie, but it's in the direction of truth. There are mathematical subtleties, especially with finite signals, but for intuition, thinking of it as going back and forth between time and frequency is spot on.
Okay, makes sense. Now, you mentioned earlier that the x-coordinate of the center of mass was only almost the Fourier transform. What's the rest of the story?
Right. Good catch.
Yeah.
That center of mass, it's a point in a 2D plane, isn't it? It doesn't just have an x-coordinate left-right. It also has a y-coordinate up-down.
Oh, okay. So we've only been looking at half the information.
Essentially, yes.
Yeah.
And in mathematics, whenever you're dealing with something two-dimensional like that, it's often really elegant and powerful to think about it using the complex plane.
Complex numbers, like with I, the square root of -1.
That's the ones. Don't let the name scare you. They're just a way of handling two-dimensional quantities. Our center of mass point can be represented as a single complex number, which has a real part, the x-coordinate, and an imaginary part. y coordinate.
Why bother with complex numbers? Why not just keep track of x and y separately?
Because complex numbers are perfect for describing things involving rotation and winding. There's this incredibly beautiful and famous bit of math called Euler's formula.
I think I've heard of that. E to the I times something.
That's the one. E raised to the power of I times some number, let's say x, EIX, geometrically describes moving x units around a circle of radius 1, starting from the right side. It's like a mathematical command for rotate. So if we want to describe rotating at a specific frequency, say f cycles per second, we can use a slightly modified version of this Euler's formula. It looks like e to the power of -2 pi IFT. The t is time, f is our winding frequency. The minus sign is just a convention used in the standard definition of the Fourier transform. It means we wrap clockwise instead of counterclockwise.
Whoa, okay. That expression looks dense. E to pi IFT. A bit dizzying.
It can look a little dizzying, absolutely. But the amazing thing is that one tiny expression perfectly captures the idea of smoothly rotating around a circle at a frequency f.
The winding part of our machine.
Exactly. Now, remember how the length of our rotating vector was set by the height of our original signal? Let's call it gf.
Yeah.
We can combine these. If you multiply the signal gt by that rotational term e2 pi ift, that combined expression ga8 pi ift, mathematically represents drawing that entire wound-up version of the graph at a specific winding frequency f. It's an incredibly awesome and compact way to write down that whole visualization we built up.
Okay, so that formula basically is the wound-up graph in math language. Now, how do we get the center of mass from that? You mentioned integrals.
Right. So think about finding an average or a center of mass. If you just had a few points, you'd add them up and divide by the number of points, right?
Yeah.
An integral is basically the way mathematicians do that same thing, summing up and averaging, but over a continuous range, like our time interval. So the integral of that complex expression, GFT E2 pi IFT, over our time interval, and then divided by the length of the interval, that gives us the complex number representing the center of mass.
So the integral is just a fancy way of finding the average position, the balance point of that continuously wound up graph.
Precisely. Even if the calculus looks scary out of context, the underlying meaning is just that, finding the center of mass of the wound up signal. The whole expression is just the center of mass of the wound-up graph.
Yeah.
No calculus knowledge needed to grasp the core idea.
Okay. We have the wound-up graph formula. We have the integral as the center of mass. Are we there yet? Is that the Fourier transform?
Almost. Just one tiny final step. The actual honest-to-goodness Fourier transform is defined by doing that integral, but you don't divide by the time interval at the end.
Huh. Why leave that out? What does that change?
Well, instead of getting the average position, the center of mass, you get a result that's scaled up. If your signal lasted for 5 seconds, the Fourier transform value would be 5 times bigger than the center of mass value. If it lasted 10 seconds, it'd be 10 times bigger.
So longer signals give bigger results in the transform.
Exactly. It makes intuitive sense, right? If a certain frequency is present in your signal and it persists for a really long time, it contributes more strongly. So, when a certain frequency persists for a long time, then the magnitude of the Fourier transform at that frequency is scaled up more and more. It rewards signals that are strong and sustained.
Okay, that makes sense. So let's recap the whole thing then, the actual Fourier transform.
Right, so you start with your signal, gt, which depends on time. The Fourier transform, often called g-hot, is a new function. Its input isn't time anymore, its input is frequency, f, our winding frequency.
And its output.
Its output for any given frequency f is a complex number. That complex number tells you about the strength, the phase, like the starting position, of that specific frequency f within your original signal gt. That complex number is found by that integral process, which intuitively represents the scaled-up center of mass of the signal wound around a circle at frequency f.
So even though the final formula with the integral and the e to the I stuff looks complicated.
Yeah, it can look daunting, definitely.
If you understand the pieces, the rotation with Euler's formula, multiplying by the signal to get the wound-up shape, and the integral as a kind of center of mass calculation, then it actually makes sense.
Exactly. You can see how this whole thing carries with it a very rich, intuitive meaning. It's not just symbols. It represents that whole process we visualized. Oh, and technically, the purest form often involves integrating from -infinity to infinity, essentially looking at the signal over all possible time. But the core idea is the same.
Wow, okay. We went from jumbled signals and unmixing paint to complex numbers and integrals finding a center of mass.
We did, and it all connects. The Fourier Transform gives us this powerful shift in perspective. From the messy time domain to the clean, organized frequency domain. It makes the invisible components audible or visible or just understandable. It's really a beautiful piece of mathematical intuition made practical.
Man, oh man. Yeah, there's clearly so much depth here. We've really only scratched the surface, haven't we? But it feels like we've seen the core magic. How this seemingly complicated math can be built from these understandable, almost playful ideas like wrapping and balancing.
Definitely.
It's a good reminder, that even complex formulas can hide real beauty and obviously a ton of practical power, turning that chaos into clarity.
And that brings up a final thought, maybe for you, our listener. We've talked a lot about this unmixing paint idea, decomposing complex signals into simpler frequencies.
Right.
So the question is, now that you've seen how this works for signals, where else might this kind of thinking apply? This idea of breaking down complexity, finding the hidden fundamental components. Where else could you use that?
Like looking for the underlying frequencies in, I don't know, economic data or social trends, or even just trying to understand a messy problem in your own life by breaking it down.
Perhaps. Keep an eye out for those hidden patterns, the subtle frequencies beneath the surface noise. Once you know how to look, you might find they're really everywhere.
Okay, so there's a human in the loop, just in case you're wondering. Everything we do is available on BioniChaos.com. Go check the website out. Let me know if there's any feedback. Don't forget to like, subscribe, unsubscribe, whatever you have to do. And check Patreon as well if you want to support this project. That's normally what a robot should say, but